So we have a probability space discretely filtered with a discrete filtration, and I take now an infinite time horizon. So I do not consider as last time finite sets of time points. And in order to be reminiscent with last time, I'm working under the measure Q, which corresponds to a martingale measure of the market. But this is only to be reminiscent. I take now a definition. So let xt be a stochastic process, let's say Rn valued. Then we call eta S U T. So these are complex valued processes adapted with respect to the variable s, yeah, first variable, and those other two variables are parameters. ut are parameters.
Is T asked to discrete?
Everything is discrete. Yeah?
Not everything. You have Rn valued.
Everything which is time.
I mean time.
Time,
yes.
which relates to time. S and T apparently relate to time. So this is discrete. T is a discrete parameter. You were right to ask, and U lies in Rn, and this in that sense not discrete, but a continuous parameter. And we will also see that without any restriction we can stay continuous in U. So when I fix an S and a T, it is continuous in U. What is the meaning of this process, which we call forward characteristic process? The meaning is that the conditional Fourier transform of the process x t, which is given, can be expressed by the value xs plus the sum k goes from s to t minus 1 eta at the point s u k. Yeah? So this is the definition of the forward characteristic. If I have a stochastic process, I can calculate the forward characteristics if I'm able to take a proper logarithm. And the proper logarithm usually means that the characteristic function is not vanishing, which is an assumption. There are characteristic functions which can vanish, but if it is non-vanishing, proper logarithms can be defined. So remark, this is a weak condition on stochastic processes, namely that the conditional Fourier transform does not vanish anywhere with respect to u. We have no zero. For instance, if the distribution is infinitely divisible, this is the case. Then it never vanishes. And otherwise, yeah, there are cases. Good, so if we have a process, we can calculate the process of forward characteristics. This is the first statement.
Can you explain what is discrete here and what is not?
Time. This time is discrete. This is discrete. And the Fourier variable is certainly not discrete. This is u in Rn. And x is Rn valued, so this is a scalar product.
So summation there with respect to which index? This is k.
Yeah, I call it k. So k, yeah.
And okay.
This is discrete.
Yeah.
So eta is at this point eta of s is a function from Rn times, and here I have the set of k in n, k greater or equal than s. So everything.
It's an assumption. So if this relation holds, then we call eta s to be characteristic.
The forward characteristic,
Okay.
yeah. And for every process, we can calculate it if this assumption.
For any process, okay. For any process, we can calculate it exactly. But if it's more complicated situation, so it's a question if you can find explicit.
True, but I just say if the process
Yeah.
has the property that the conditional Fourier transform does not vanish, then the eta is well defined. I do not say that I have formulas for it, but
Yeah.
it is well defined.
Yeah.
So it's like a characteristic of a semi-martingale which is defined for semi-martingale.
Yeah.
This is the discrete version of it, but the forward version of it. So how is it related to characteristics of a process? This is the first question.
So here is in the most general situation.
Yeah,
Very complex.
right.
Okay.
What would be the discrete version of a process characteristic? So if you adapt the general definitions in, let's say, Shakotchi-Yaev to this particular situation, you would say the process characteristic is nothing else than the conditional Fourier transform of an increment along one step, conditional on Fs, and we recognize it immediately that this is eta s u s. So the discrete version of a process characteristic in the sense of Shakot and Cheyaev is the short end of our forward characteristic curve. Short end, I mean the left end of this curve, because it starts being defined for s, and then it is defined s plus 1, s plus 2, and so on. So at the most left point, this is what would be the process characteristic. Yeah? Good. I want to write a proper definition of a process characteristic, just to say it. So x equal to xt has characteristic kappa of x if, yeah, I write it in a little bit different language, but it is apparently the same. Is that what I want to write? Yeah. Yeah. Kappa of x, u, and k. That this process with respect to s is a martingale. This is called the process characteristic of x. And corresponding to our setting, we would say kappa x u k. Yeah, this depends certainly on k. No, sorry. I write it like that. Equals the eta of k u k. So the process characteristic in the sense of the theory of Shakot and Sheyaev is a stochastic process with respect to this discrete variable depending on a parameter u. Yeah? And if I evaluate that, it encodes nothing else than the conditional Fourier transform of the next increment. And I just wanted to introduce that notation for it. Yeah. So this I call the process characteristic because I will need that notation later. Now the question is, the important question is, given some complex valued process eta, which depends on two parameters u and k, or u and t, such that I have the processes from 0 up to time t, adapted complex valued when is this a forward characteristic process? When do I have that? So the question is, I give you an eta, and I would like to know which conditions have to be satisfied such that I can say there is an x, and I can do that. This would be easier for characteristics in that sense, because those characteristics are simply nothing else than adapted processes with respect to the variable k and logarithms of Fourier transforms of distributions. You have at every scenario up to time s, you have a distribution.
Does this theory defines the process from?
In law. In law.
So this is, for Levy processes it has some special form.
For Levy processes it is constant. Does not depend. It's deterministic. Not constant, deterministic. Even constant. For a Levy process, even constant, there's no time dependence. But for, let's say, an additive process, it would be time dependent in K, but still deterministic. And for a general process, it is neither deterministic nor independent of time. Yeah. So I would say to say how characteristics look like is a little bit easier because there is no redundancy inside. Here there is redundancy. There's too much information, so we have to connect it to each other. This is what we will learn in the next theorem. When it comes from a stochastic process, it satisfies a certain property, and if this property is satisfied, it comes from a stochastic process. So this is this... huh? No. This is much more general. How did I formulate it? Yeah. First, I introduce one definition, which I call decomposition property. Because otherwise it would be very hard to say, to formulate a statement. What is the decomposition property? The decomposition property tells me something about the process I am considering here. It tells me that the process has a drift part and something which I would call a martingale part. So this holds for s less than t, and I have this decomposition property with respect to epsilon t. This is an RD valued martingale. Yeah?
I really don't understand this sum because should it start from S and goes the
No. This is
one?
this is just the discrete version of.
Yes, stochastic integral. I do understand it.
Yeah.
But that's what I am asking.
That's not a stochastic integral. It's a differential. It's just here I have let's say a d-dimensional Brownian motion.
Yes.
And here I have vector fields in front of the Brownian.
Exactly. So my question is, okay, maybe I'll write because I can't understand it.
Yeah, but there is an error here. Maybe you mean that
Yes.
it should be S here.
Okay.
Okay.
Yes. And the summation, I can't. Oh, I see. That's. I think that summation
No.
okay, now
it's not a stochastic integral. It's only a differential.
Yeah, now I understand.
It's like when you write a stochastic differential equation with a couple of Brownian motions.
That's okay.
You see?
Yes, it's stochastic differential. It's just one step.
One step.
Increment.
Yes,
Okay.
I can do that here because
Yeah,
it is discrete.
exactly.
So
That's why I didn't understand.
very good. So you see, I start with that decomposition property, and under such an assumption that my process is generated in such a setting, I can make a statement now. This is what I want to do.
It would be better if you write just simply the inner product there, and
I used the inner product already.
Yeah.
And this is different. This is the inner product of
Yes,
two
different,
geometric objects.
yes,
And
yes,
this would
I
be,
understand.
this is not really an inner product, this is just a summation
It's
of...
exactly inner product of increment and this
Right.
vector. Which
Yeah, it is an inner product, but somehow philosophically different one.
Yeah, sure.
Yeah. And in order not to write a second notation,
Okay.
I do it. Welcome. Might be difficult to follow now.
No, I think I will follow.
Okay. So I just to introduce you quickly, I'm probability space discrete filtration. I look at stochastic processes with respect to a discrete time parameter, and I defined a new notion which is called forward characteristic process. And this is nothing else than a process eta being complex valued, satisfying this equation. So this is nothing else than the logarithm of the conditional Fourier transform of the increment and somehow differentiated in this discrete sense. And I ask myself now, which properties are satisfied by those forward processes? Because apparently there's redundant information, so you need some properties to be satisfied for that. I look at the forward process which satisfies such a decomposition property. And the theorem I want to prove now is the following. So I have an x and an eta. And I want to say the following statement. Eta is forward characteristic process of x if and only if one thing we already understood, the characteristic of the process x at time s equals to the short end of this process eta, and this is now a more delicate property. Let me write it down. If I take the characteristic of the process x and I subtract the sum k from s to t minus 1 of alpha s uk, the integrals are here always with respect to the parameter, like in the Histrow-Morton theory, if you remember. Jana. This equals to the characteristic of the process x together with epsilon, the martingale. Here I have now n plus d dimensional. Yeah? In the n dimensional I have a u, and in the e dimensional I have minus the imaginary unit of the sum k goes from s to t minus 1 sigma. I make a dot here, s u t s u k. So this here is a vector in c to the power d, and is just what I can insert here.
The composition property is not always true. Yes, it's an assumption.
This decomposition property is an assumption, right? The decomposition property is an assumption. Yeah? And the kappa always depends on S. And this property holds so you see that there is a relationship appearing which tells the characteristic of the process x minus a functional of the drift equals the characteristic of the process x together with epsilon having that relationship. It's a non-trivial relationship. So if x and eta fit together in this strong sense, this has to be satisfied, and if this is satisfied, they fit together. That's the statement. Yeah? Just to make you feel comfortable with this statement, then we prove it. The goal of today's lecture is to understand this statement. So, example and the definition. We make a very simple case first. This is called the case of local independence. Local independence is defined via the following property. We are just in the setting of the proposition, of the theorem. So this logarithm of the Fourier transform of the increments of x and epsilon, this is simply a sum of the two increments, which means nothing else than that the increment of x and the increment of epsilon are conditionally independent. They are not independent, but conditionally independent. Conditional independence. Of increments of epsilon and x. Under this assumption, the conclusion of the proposition is much easier, because then you have here at the left-hand side kappa x epsilon. This is kappa x of u, which you have at the right-hand side. So that you can cancel that. I do it from time to time to write an integral such that everybody feels remembered. And here I have kappa of epsilon s of the second slot, which is the guy here. Yeah? Now we do another specialization. Assume for a moment that epsilon is Brownian motion. And let's say, simply a Brownian motion. Even one-dimensional. Then the kappa of epsilon, in time is the natural numbers, 0, 1, 2, and so on. The kappa of epsilon at time s is then minus v square divided by 2 times t. Yeah? So this reads then, this property is then k goes from 0 to t minus 1, alpha s uk is equal to minus I squared and I made a little error. It's not a t here, it is a 1 here, because it's only the increment. It's the differentiated version of it. So that's all, and this is precisely what you would call the His-Morton drift condition for discrete.
In terms of Fourier transform.
The His-Morton drift condition is by itself always written in terms of Fourier transform. But it is only evaluated for u equal to I. I will show you that example. But this is, I want to make the point that it is just that. Yeah? So this is a very familiar situation. But why not doing the example right away? Then everything is clarified. What is a typical case where we have local independence? Assume that the process x of t is predictable. We have a predictable process. For instance, x of t could be written as k from 0 to t minus 1 r of k, like an integral with respect to a short rate. Then this is a predictable process, not adapted, but even predictable. a predictable process is locally independent of any martingale. Why? We have to check whether the conditional Fourier transform of xt plus 1 minus xt plus some martingale increment, that this is equal, we have to calculate that. Since this is predictable, the xt plus 1 is ft measurable, so I can put it outside. Yeah? And I have here the kappa of epsilon v at time t. By predictability.
This is another example of what?
This is an example where I have local independence by itself. Yeah. Just want to look something. Sure.
Epsilon, this is about this product characteristic.
Yeah.
Why do you combine it with the process example? And this says something about the process.
Say it again. Why do I combine what?
Just
Why do I study the process eta?
no, okay. But why you combine the process x and epsilon, and this says you something about
No, it's the other way around. I want to know if you give me a process of etas, whether there is an x to it. Because this is just a situation which we have, for instance, in option markets, that you see a lot of option prices. This gives me a process of etas. And I would like to know what is the good model to choose which works together with those option prices. So in fact, I would like to know how to write a model for option price surfaces. This is nothing else than writing a model for eta, such that there's an x behind. And this is explained by that theorem. This tells me this is a forward characteristic process of some x, if and only if such a condition holds.
So eta you know somehow from prices. Okay, you know.
Eta 0 I know from prices. But I want to have a dynamics for it, because otherwise only having eta 0 just tells me what is the option surface today. But in reality, I observe every day an option price surface, and I need to have a dynamic idea how these surfaces move. And in my opinion, that's the easiest way how to express this movement.
And this helps you to construct characteristic of the process x.
Yeah, in particular, it helps me to construct the characteristic of a process. But it is more information.
Is this one-to-one correspondence? Okay.
If I have a process, I get an eta, and if an eta which satisfies such a condition, I get a process. And now coming back to your question, in order to express a condition, I need to have a process which is somehow, which has a drift and a martingale part, and to talk about the interaction of those two parts. This is always in mathematical finance when you have some martingale property, you have an interaction between a drift part and the martingale part. This is how you express it. If you were not specifying that, it would be hard to say. But you can always specify the conditions in terms of a Ito decomposition, and that's the discrete time version of it.
Doesn't always give you this decomposition property. So it comes from the market. So this is option prices.
Yeah.
And this decomposition, is it?
No, this is somehow an assumption. I assume that I have some martingale, let's say Brownian motion, which drives the evolution of option price surfaces. Might be anything. I mean, it is just a very, it's in my opinion, a very innocent assumption which looks difficult, but in fact it's only the assumption that you have an Ito decomposition with respect to some driving noises. It's nothing more. It is like when you make statements about classical models in mathematical finance, you say, well, I believe that my logarithm of a price process is driven by a Levy process. Then you write a stochastic differential equation by this Levy process, and then you ask, what is the condition such that this is a martingale, so e to the power the solution is a martingale, and then you get the drift condition, which relates the drift and the martingales, which drive together. Nothing else. Let me fix here what we finally have. We have E U R T plus kappa epsilon TB. So this corresponds to the kappa x of U, and this is the kappa of epsilon. And so you see that you have this local independence condition satisfied. And this is precisely the His-Morton situation. And therefore, this is precisely the His-Morton drift condition in that case. It was only generalized a little bit. So you see, it is somehow a sweet way to talk about all those things without too much technical raffinesse. You can write down everything. This is practically assumption-free. So this is the local independence case, and it should tell you that this is the proper generalization of local independence when x and epsilon are not locally independent. Why do I need that it is not locally independent? Maybe you heard of the effect which we always have in stock markets, leverage effect. So this is a dependence, a relation between changes in underlying prices and changes in volatility. It speaks about the correlation in the simplest case of increments of volatility and increments of the underlying. And in some markets, this correlation is measured to be 0. In many markets, it's negative, and quite strongly negative, negatively correlated. And this effect is just here. So if we have a leverage effect, this will be a non-trivial guy, and it will not be locally independent. If there's no leverage effect, the nature of the increment in x does not at all influence the increment in epsilon. Good. So that's the statement I want to prove. The formulation is proper, and you will be surprised. The proof is very easy. It's very easy. It's almost there. The work in that field is to formulate the theorems properly. If you are not doing that, it looks like a big mess, and I think it looks a little bit less like a mess now. It is somehow cleaned up. Jan Carlsen and Paul Grüner were doing the continuous time version of it, and there it also, it is, I think, optimally written, but you have the impression that after, let's say, 15 pages of that article, you arrive at that relationship and you're really exhausted there. Because there are a lot of technical assumptions when you can insert that here, and so on. And it's not only that, it's also the discrete time formulation is a huge advantage here. So let me do the proof of that. Yeah.
This say somehow about what does it say about dependence between prices, auction prices, and the process?
They can be dependent, but the increments are independent. You see, I give you an example of locally independent structure, which also Jana did, I think, in the course here. So this is now a parameterized model, but still it is of the same. You have the same structures appearing as here. When you take a Heston model, the Heston model has 4 parameters and 2 initial values. The initial values are x0 and v0. This is the log price and the initial variance. And the parameters are kappa, theta, sigma, and rho. And rho is the correlation between W and B. Yeah? And the case of local independence corresponds to rho equals 0. This means that the increment of this Brownian motion has nothing to do with the increment of this Brownian motion.
So this epsilon corresponds somehow to V?
The x corresponds to x, and somehow this corresponds to the eta. And the epsilon corresponds, as you said, to the W. Yeah? So you would say in that case, the characteristics of the process X and V, yeah, U1, U2, split. Yeah? To split into 2. If rho is equal to 0. Local. It is mixed. This is the leverage case, when you have a non-trivial correlation between the 2 components. But also it does not mean that the x and the v are independent. The increments are conditionally independent, because apparently the x depends on the value of the v. Yeah, they are not independent. Yeah? So this is what is meant. This is what you should have in mind. Good, I clean again the board. Now, for the proof, we give ourselves x and eta forward characteristics of x. Yeah? We give this to ourselves. Then we have the following equation satisfied. We know that that this holds true by definition. This is how I defined the forward characteristics. This is the equation because the forward characteristic is the logarithm of the conditional Fourier transform of the increment. Hence, the right-hand side is a martingale. With respect to S. And if it is a martingale, there's a certain drift condition which we should see. Yeah? And I evaluate now that condition by inserting what I have here. So I just write being a martingale is equivalent that x s plus 1 minus s plus, and now I have k to t minus 1. I have eta s plus 1 u k minus eta s u k. And now the sum is a little bit too long. Sorry, I go here from s. The first one should only go from s plus 1 to t minus 1, but it goes from s. So I subtract eta s u s. And the second one should go from s, that is okay. Being a martingale is equivalent to the statement that this is 1. Yeah? The right-hand side is a martingale if and only if this is equal to 1. Now I insert the equation I have for the eta here. This equation which I have upstairs. So then I obtain exponential I u x plus 1 minus x. Then I have a sum, and I write it first with the epsilons. Sum I from 1 to d, sum k from s to t minus 1. I have a sigma s I u k times the delta epsilon I of t, and I put that inside, then it gets nice and visible. Then I have the alpha. This is just the sum k from s to t minus 1 alpha s u k, and minus the eta. This is equal to 1 conditional on fs. And now you see precisely the definition of the characteristic. You calculate the joint Fourier transform of the increment of x and of the increment of epsilon at the point u, and here you have minus imaginary unit and this vector, and therefore this guy here should be equal to this guy. Mm-hmm. So the kappa of x epsilon at the point s at this point should be equal to this guy here minus the alpha, and that's it. That's the martingale, nothing. There can't be anything more. Also, again, you see, in comparison to the theorems in continuous time, everything falls out in a very, very easy way. This whole derivation of the Histoire-Morton conditions, of more general conditions in discrete time, it's practically assumption-free how you can do that. So you see, it's just a martingality. It can't be more. You have to come to the situation where you can read off the kappa, and then you get this relationship. Yeah? And certainly, when you look at it the other way around, you have an eta satisfying this condition, then you just go back and you receive that this is a martingale, and therefore it is, that's the statement. Yeah? If this is a martingale, you obtain that eta is this forward characteristic process of X. So this is now somehow nice because you have characterized if eta satisfies such a type of decomposition, and if the alpha and the sigma are related via those formulas, then eta is the forward characteristic of the process. And this is nothing else than the Hiestrom-Morton condition for this setting. Yeah.
In continuous time, do people assume that the option price has jumps?
Yes. I mean, here it is by default that you have jumps because it's a discrete time setting. You have fixed. Yeah. But in continuous time, sure. The condition in continuous time is precisely the same. It is just that you replace sums by integrals. You replace the process characteristics by the predictable characteristics in the sense of Charcot and Cheryaev, and you define the forward characteristics with the same equation, but you replace it by an integral, so the sum.
So the option price has jumps and the underlying.
Yeah, as it should be. Yeah.
Some are different. For example, underlying has jumps, but this option price.
Yeah. Usually it is like that. People would like to use more sophisticated models because they see from the observation of the time series that it can be the hypothesis that there are no jumps in the time series can be rejected under very weak assumptions. So there are for sure in many assets where we have a good amount of data, you can check that there are jumps in the time series when you make a certain model assumption. And it is even worse, you can check that there are jumps in the variance process. So this is somehow an econometric fact. Why do people not often use such models? Because they are very delicate to calculate with. If you have jumps in the variance, all the formulas usually break down and you cannot do modeling well. In a way, this approach also tries to help in this direction, because we are trying to be as general as possible in our starting assumptions, and we are not really heading for analytic formulas here. We just write the proper discretization, which can make things a little bit easier in some respects. Second example, this brings me just to this option pricing question. So let's assume we have only one guy. The X is one-dimensional. This is just what I wrote yesterday, but I want to write it again for the sake of appreciation of the theory. S UK. Right. So
for U equal to 1, but D equal to 1.
n is equal to 1. Sorry.
It's n.
N, yeah. I'm sorry. I just have one guy I consider now, and x1 should be the...
Till now the dimension was d, that's why.
The dimension of x was n, and the dimension of the factor driving was d. A d-dimensional Brownian motion and n-dimensional process x. I try to keep these things different, even though there's a tradition not to do that, but I like when they're different, coming from an hypoelliptic world. Yeah.
Sorry,
Yeah. No. It's very good. So think here of the logarithm of a price process x, which is a Q martingale. So this means that this is Q martingale. I just want to make the statement that under a slightly more general assumption, which I usually write like that this is integrable. So I have exponential moments of this order 1 plus delta. Delta is greater than 0. I can extend nicely my definition of eta to the strip R cross minus 1, 1 imaginary unit. That my etas are defined there, because the conditional Fourier transform is in fact the conditional Fourier Laplace transform. If I have the exponential moments, I can go a little bit away from the complex axis into the real axis. And the real axis corresponds here to an I. Yeah. Okay, so I have my eta defined there. What does the martingale condition mean on x? Martingale condition means nothing else than the eta of minus I and k is equal to 0 for all s less or equal k. This is the martingale condition. Yeah? And you can see finding a process such that at minus I you always have a 0, satisfying those properties corresponds just to describing a process of marginal distributions of some process x. And this is what we need in option pricing theory. In option pricing theory, you would like to write a dynamics of, let's say, families of marginal distributions. So when you do option pricing, there is one easy way how to do it, but this easy way has a lot of flaws. The easy way is the Dupere formula. I give you option prices today. You interpolate and extrapolate the option prices by some parametric method. You obtain something which is nicely differentiable, and then you apply the so-called Dupere formula, and this gives you one model X, which has the property that for s equals 0, so this means today's prices, they fit just to what I observe in the market. And it also gives me a dynamics, so you could calculate this out of it. So in mathematical finance, so far we have one standard model how to take today's option prices and get a dynamic of option prices. What is the disadvantage of that? The model is highly non-realistic. So it is driven by one Brownian motion, therefore it is complete. It is free of jumps, so this means the econometrics is immediately rejected. You don't believe in that econometrics. And it has this so-called local volatility structure. So the volatility only depends on the level of the price or the log price. So there are a lot of highly non-realistic aspects in it. You can compare that to the following situation in interest rate theory. When you do interest rate theory and you go to the market, let's say to the European Central Bank, you see this yield curve today, then you can also say there is at least one model which produces that yield curve today. This is, I take this yield curve and the dynamics of the model is shifting it to the left. So it's a deterministic model. This dynamics is fitting to today's market situation. It reflects perfectly today's market situation, but it is econometrically wrong because it does not explain any stochastic movement. Dupere formula is somehow the generalization of that model in the world of option prices. It also explains today's prices well, but that's the only thing it does. The econometrics and the dynamics is not right. This has an impact. This has an say the sentence to the end. A consequence in industry. In industry, therefore, there is a recalibration done every day. So the Dupere model you fit today and the Dupere model you fit tomorrow are different, and you always believe on a model of your day, and in the evening you throw away the model. So in fact, you could conclude out of that there is no modeling in a lot of realms of investment banking. This is a different approach. There we try to say we would like to understand all models which explain my surface today and ask which ones are the good ones for my purposes. It's a little bit different point of view. Good. So this is the relationship to option pricing. Please, Elena, ask.
As far as I understand, the Dupere formula helps to calibrate just to
Today.
to continuous models.
Yeah?
So models with continuous realizations.
It is finally the case, yeah. So the Dupere model takes the eta 0 in our language and translates it into a local volatility. What you are saying is completely right. If this eta 0 comes from a distribution which is now, let's say, we have continuous time, and at the short end we have jumps. So the Levi-Kinchin decomposition at 0 has jumps. Then the local volatility will explode at the short end. But that's not the only problem, that you cannot explain jump structures with that. There are other problems too. Yeah? I just wanted to make the point. The option price surface goes into this today for S equals 0. And the Dupere model translates this into local volatility. We do not do that, but we rather say we take today's option surface and we ask for all possible x which are compatible with that. And therefore we say we take the eta 0, make a stochastic evolution into the future, and ask whether this stochastic evolution into the future is compatible with the process or not. And this is the condition which is to be satisfied.
But do people still use Dupere model?
Yes, every day and everywhere in the world. The reason is that there is no well-tractable alternative.
And this is not yet well developed.
I would not say that this, no, it's by far not. It's not enough developed. But people try all the time to come up with models with this approach. So this is popular to try it. But so far it was always the case that it is much too complicated as soon as you take the pen into the hand. And I hope, what we try to suggest is this discrete time approach, which so far I hope to convince you is not very complicated. For instance, what do people do? one very popular approach is to say, I can translate my surface today into a local volatility. So I know that local volatility, if it is deterministic, is not good. So I take a process taking values in local volatilities. This is what Sergei Nadocci and René Carmona did, and I think it was Sergei's PhD thesis. So they write then a stochastic differential equation in local volatilities, which is by itself a nice idea, but it immediately leads to a very, very ugly equation. You can imagine that the no arbitrage condition for local volatilities looks very unfriendly. This is not of this friendly His-Morton type, but this is a very wild nonlinear transformation of that. And therefore, when you look at this paper, which is a nice and good paper, the no arbitrage condition, even if you are familiar with all of stochastic analysis, is not immediately revealing to you what it means. It's complicated. Second, there is no existence and uniqueness theorem for that equation because it is so nonlinear that we don't know if it exists. Solution. And you cannot simulate from that equation. So therefore, it does not make much sense to develop this equation if you cannot do the basic thing you would like to do when you do such a theory, to simulate from that equation. This is the minimal requirement you have for a model in mathematical finance, that you should be able to simulate the trajectory of the model. Here, this is completely different. When we have such a process eta, I can simulate it even on a small computer. I only need to obey the relationship between sigma and alpha and always think in Fourier transforms. Yeah. You could say, if it works in Fourier transforms, it should also work in local volatilities. I argue not necessarily, because local volatility is something very special. So we know a couple of local volatility models, and for those models, we could maybe write down a nice dynamics. But we know a lot of models where we can write down a nice dynamics in the Fourier side. So it is somehow a good parameterization of the problem. Local volatility is a very non-linear way to encode the information from eta 0. Therefore, it is problematic. It's like in geometry and mechanics, you have a high-dimensional problem. The high-dimensional problem is, let's say, spherically symmetric, but you are working with cylinder coordinates. Then the equations suddenly get very unfriendly, and when you look at it from that point of view, you see not much. You transform it to the correct coordinates and things get easier. I would compare that. So I think that the Fourier world is intelligent in this type of reasoning because we always have this local decomposition structure, and for conditional Fourier transforms, this is tailor-made for conditional Fourier transforms. Yeah. Well, okay. So this is what I wanted to say as examples here. Now let me show you that there are actually a lot of models which where we can write down precisely the forward characteristic process. There are many models where this is possible. In contrast to local volatility, where we do not have so many models where we can write down the forward characteristic process. Maybe I clean both of them right away.
Is this discrete version of this theory written somewhere? Or you just
Not yet, no. It's not. I would say in econometrics there is a very an overwhelming majority of models is written in discrete parameterizations. Gauge models and so usually are written discretely. In mathematical finance, there's a tradition to write things in continuous time, which started with Black-Scholes, and a lot of formulas is an offspring of that. There are good reasons to do that, because continuous time means that you're talking about many discretizations having an asymptotics, and for the asymptotics you can use methods of analysis. This is good. Nevertheless, one should not forget that sometimes it is considerably easier to write things down in continuous time, and it's sometimes very insightful to do it. As I said yesterday, I probably would not give the talk here, nor would I write an article about it if I were continuing doing it in continuous time. Because in continuous time you get the impression that things are not, it's not worth doing it, because it develops a level of sophistication and of complication that you are not really seeing what is going on. But in discrete time, so far you would say you could have given the talk yourself. There's nothing particular happening, even though we derived the same equation. Yeah. So, what are the many models, what I claim, where we can write down the forward characteristics directly? These are so-called affine processes. Let me just give you the definition. I have a family of stochastic processes taking values in D, and this is a subset of Rn, and I usually take it convex and closed. And I assume that the following conditions hold. First one, Markov property. It's a Markov process, and second, I mean, you could conclude from the second the first one, but I write it nevertheless separately. The conditional Fourier transform can be written in such a way. For all x in D and what is U is an element of a set capital or calligraphic U, and this is a union over UMs. And what are the UMs? These are those U in C to the power n such that this guy the sup over x in D is less or equal than m. So the geometry of DD is convex, yeah. So this is a reasonable set to talk about. So you're looking on the complex vectors such that on this set you have this is bounded by m, and then you take the union of those guys. This means for each u, the e to the power iu is bounded by uniform constant, and therefore you get an um continuity of the phi and of the psi. on um, and what additionally we assume that the psi ut is equal to u if the t is equal to 0 and the phi u0 is equal to 0 and for u and u. So this is called an affine process, a Markov process such that the conditional Fourier transform or conditional Fourier Laplace transform is exponentially affine in the process itself. Yeah? And you can make a very simple conclusion here. You can right away say that no, I write it on the other blackboard. I'll write it here. X an affine process, then we can calculate the characteristics. And the characteristics, yeah, I made a little error, I'm sorry. There's always t minus s and there's t minus s. The characteristics are phi u t minus s plus psi u t minus s x s. These are the characteristics of the process x, starting at little x. And yeah, I need to subtract additionally this guy. This is by definition. So for affine processes, you can immediately write down the phi and the psi. You can immediately write down the forward characteristics in terms of phi and psi. Phi and psi additionally satisfy the flow property. So this means the psi of u, psi and the phi of us plus phi of psi ut ust is equal to the phi of t plus su. Yeah? The cocycling property. Why is that true? Because of the Markov property. If you take the Markov property and you apply it here, or yeah, Markov property. I would even say, as I write it here, it's nothing else than the tower property of conditional expectations. So when you calculate xi uxt on fr, you can also calculate that xi uxt on fs and this on fr. If you calculate the left-hand side, you obtain an expression. If you calculate the right-hand side, you obtain an expression. They have to be equal, and therefore you obtain this property. Yeah.
Is it really necessary that it will be uniform in time? I mean, that psi depends on t minus s?
No, it's not. Very good question. It is not. You can do this. You could write s comma t for phi and for psi. I just want to insist on this time homogeneous version of the affine processes because I will only use a particular version of time inhomogeneous ones, namely the ones where the phi is time inhomogeneous, but the psi I stay time homogeneous. Yeah, this has a reason why I do it like that. So out of this flow property, you can define difference equations when you define yourself a function r like that and a function f like that, you see immediately out of the flow property that psi t plus 1 minus psi t u is equal to r of psi t u, and phi t plus 1 u phi t u is equal to f of psi t u. Right? With initial value psi 0 u is u and phi 0 u is 0. As I said it before. So it's just an intelligent way to encode these equations into two difference equations. Also, to make a comparison to the continuous time theory, it's also funny because a good part of my scientific life I was fighting in continuous time with the question, which looks very innocent, if this equation is differentiable with respect to t in continuous time. Because we only know at this level that it is continuous in u, and under the assumption of stochastic continuity it will also be continuous in t. But we know that this continuous equation of this cocycle type is not necessarily differentiable. There are well-known examples which are related to the fifth Hilbert problem. So this is a whole theory which people have been working on for a very long time. We managed to prove in the case of continuous time affine processes that it is in fact differentiable, but this took a long time and it's difficult, as a proof is difficult. Here you see.
But you need some assumptions on either your model or
The assumption is that the process is affine, stochastically continuous. The state space can be general, so not even convex. And that's it. It follows general. It's a general fact. The reason is that this psi is not any continuous semiflow. It is a continuous semiflow of logarithms of Fourier transforms. And these are very particular functions, and you can play with that. But it is, nevertheless, it's a delicate theorem. It's a very delicate theorem. In the standard theory of affine processes from the beginning of the 2000s by Damir Filipovic, Walter Schachenmeier, and Darrell Duffy, they assume that it is differentiable. Then it is easy. No, it's difficult enough. But then the problem is easy. Then you get the Riccati equations. But if you do not assume this differentiability, it was unclear. Is there a counterexample or is it always true? And we proved it's always true, but it took us a long time. And I was somehow amazed when I first wrote the discrete time theory, which by the way has been written also by other people, Jerzy Sapczyk and also Damir, where everything is somehow, there's no problem anymore. Yeah. Good. So these are the affine processes, and for those affine processes we certainly have a very nice forward characteristic process. What are examples of affine processes? Often for my students I formulated the other way around. what are examples of processes in mathematical finance which are not affine? Yeah. So every Levy process is an affine process. Yeah. Every Ornstein-Uhlenbeck process, Gaussian or non-Gaussian, is an affine process. The Coxingers-Ross process is an affine process.
Okay, that shows is not an affine process.
Yes, but it is a deterministic function of an affine process. So the log-normal distribution is not,
Okay.
I mean, to be precise,
Yeah.
log-normal distribution is again infinitely divisible. So if you look for a Levy process which has this as distribution, you can still find a Levy process doing that, and therefore it's affine. But if you look at the dynamics of exponential Brownian motion, this is not affine. But it's a deterministic function of something affine. So this, I mean it like that. Can you tell me a model in mathematical finance which is not a deterministic function of something affine? That's not so easy. So the main example is the so-called Saber model. Stochastic alpha beta rho model, which is a variant of the generalization of the CEV model. So these are local volatility models where you have a particular non-affine structure in the beginning. These are the examples. Yeah? And these are, I would say, the main used examples. A lot of other examples have this affine structure. Yeah? And therefore, it is interesting that for those models, we are able to write down our forward processes explicitly. Yeah, this is somehow, in that sense, important statement. Good. I do not want to overwhelm the audience, and we make a break.
Maybe you can give us some announcements for the next lecture.
Some
Announcement is.
what I'm going to do tomorrow. So you see, my goal is tomorrow. As the whole lecture, you cannot find this anywhere. I want to write a stochastic differential equation for eta and propose a solution and implementation. So this means also simulation concept for it. And so the idea is the following. I write this stochastic difference equation, which is somehow the general version of the Heath-Morton equation of interest rate theory. And I tell you that there's a certain solution concept for this equation, and which will be easy to be formulated. These solutions are solutions which are solutions of a stochastic difference equation in an infinite dimensional space, but nevertheless have the property that they come from finitely many factors. So you have a finite dimensional Markov process and the deterministic function giving the solution. If this property holds true, then the conclusion will be that the factor process is in fact affine, which is a little bit funny. So the affine processes appear even out of as a conclusion of this equation. And then I make a statement saying that affine processes we knew. So it is not, the whole theory was not developed to stay with affine processes, but to go a little bit beyond. And then I explain relationship affine processes satisfy, which is called Hall-White extension, a very well-known method in mathematical finance. And I'm able to concatenate then affine processes on one or more time steps in this discrete approach, and to obtain somehow general evolutions which are still, which can be implemented, because they are they are consistent. It's a consistent way to, for instance, use a Heston model, which is an affine model, change the parameters of the Heston model along the trajectory of the evolution and still stay consistent, which is funny.
We will not change to packing.
No, everything is discrete.
Stochastic differential equation will be like this with computation property.
Yes, always like that. Which I find, I mean, it looks more special, but it is not much more special. So, yeah, it's a discretization. Okay, good. Thank you.